So in chapter 31, we start with some basics of circuits. And from Regents Physics, you know that we use symbols in order to create these schematic diagrams. And some of the symbols are here. The first one we have is a capacitor. And the capacitor in the drawing, both of the lines are equal in size. The next one we have is a battery. The longer lines do represent the positive terminal and the negative terminal being the shorter line. Here we have just a wire, kind of silly. And next we have a resistor. We don't get too crazy about how many squiggles you draw on the resistor. Next we have a lamp. Circle with a little twisty, turny symbol there. Here we're just representing that there is a junction. Usually draw junctions with a dot at the junction. And then last we have a switch. Okay? You should be familiar with most of those. For your schematic drawings, you use straight lines and not the curved wire as you would see in the actual circuit. So now we're going to review Kirchhoff's laws and basic current in a circuit. So you have to remember that it's important to analyze each element in the circuit in terms of the current going through it and the potential difference across each circuit element. So you also know the junction rule, which means that the sum of the current into the junction has to equal the current, or sum of the current going out of the junction, and that's by charge conservation. Also, the total voltage in the loop has to add up to 0. And we're going to talk about this a bit more in the slides to come. So in a closed path or loop, the energy is conserved. So basically, if we're coming back to the same point and the displacement is 0, then the total energy has to also be 0 because we're ending up at the same point we started in. So using Kirchhoff's loop law, we talk about how the current flows through different elements and what happens to the potential difference as the current is going through these elements. So if you look at the tactics box on page 893, you're going to see how they explain the decrease in potential or increase in potential depending on the direction of the current. So we talk about the current running downstream. In other words, it would be going from a positive potential to a negative potential for downstream, and for upstream it would be going from a negative potential to a positive potential, which seems logical. So that's going to come into play with how we add up the potential difference across each element in the circuit. The basic circuit includes resistors, batteries, and that's about it. So commonly resistors are known as loads. They'll ask, if the load is 4 ohms and the potential difference is 6 volts, determine the current. Also, the battery, and you've heard me call it this before, is referred to as a source sometimes. These are kind of like old school terms, but they're still used. So we have a simple series circuit with one resistor. We have the source or battery. I drew it as a cell, and then we have one resistor. So just to reiterate what's happening with upstream and downstream, and you can refer to the battery at first because we do need to discuss what happens in the battery. The batteries the charge is moving up that escalator, if you recall from chapter 29 and 30, that the charge is moving up the escalator. The battery is doing work chemically on the charge. The charge is moving to a higher potential. So it's moving from a negative to a positive, which means that it's gaining energy, and upstream, going from negative to positive is upstream, so the battery's potential difference is positive. We call this, and this is for an ideal battery, and we'll talk about ideal batteries first, non-ideal batteries a little bit later in this chapter. But for an ideal battery, we'll assume that the potential difference across the battery is the electromotive force, aka electromotive force. Okay, and that it's positive. For resistors, though, the resistors are going from a higher potential to a lower potential. So as the current runs through the resistor, it's going from a higher to lower, so therefore it's referred to as going downstream. Since the potential difference is decreasing, you see the negative sign attached to the IR for current and resistance. So if we look at the loop, if we have just our simple series circuit with the battery and with our resistor, referring back to our drawing here, then we go upstream through the battery, which is a positive electromotive force, and then we follow downstream through the resistor, which would subtract or lower the potential difference. And so we see the negative sign in our formula here as we're subtracting the potential difference through the resistor. The sum of the potential difference has to equal 0 because energy is conserved. Okay, in this example problem, we have 2 resistors and 2 batteries, and we're going to look at the closed loop. We're going to pick a direction for our current. We may find that this current is negative, or we might find that it's positive, meaning that it's in the direction we chose. If it's negative, then it's in the opposite direction we chose. So usually we pick the current to go clockwise. That's very typical that we do it that way. Okay, so we're going to allow the current to go around the loop in a clockwise fashion. So we can see that in the closed loop, we have the sum of the potential difference, which is going to equal 0, is equal to the 6-volt source. So let's write that in terms of the first battery. We'll call it B1. And then we have the potential difference for the first resistor. We'll call it VR1. And then we have the 9-volt. We'll call that VB2. And then we have the change in potential for the 2-ohm resistor. We'll call that VR2. So for the 6-volt battery, we are going from negative to positive, so that's a gain in potential. So that's a positive value, so we'll just say positive 6 volts. Then we have the 4-ohm resistor. The 4-ohm resistor is, we don't know the current through it, but the 4-ohm resistor is going to decrease in potential. So we have a negative I times 4 ohms. And then we have the 9-volt. The 9-volt goes from positive to negative, so we're actually decreasing in potential again. So we're going to subtract the 9 volts. And then we have the 2-ohm resistor, which, again, we have a negative value because we're decreasing the potential for the resistor. We don't know the current, so we'll call it I. Make this a little clearer that it's a current. And then the 2-ohm resistance. So 2 R times I will equal our potential. Okay, and we can set this equal to 0. And using this loop law, we can solve for the current in the circuit where it might not be so apparent in the past. So we have 6 minus 9, we have negative 3. We have negative 3, plus we have, we can pull out the negative current, and then we have 4 plus 2 for the resistance. And yep, that should be correct as far as my math is concerned. And then we have 6I. We'll say that negative 6 I is equal to 3, and then we can divide by our -6, and we find out that the current in this circuit, or closed loop, is negative 0.5 amps. So the negative sign is just telling us that the current we chose, the direction of the current we chose, is actually the opposite direction. So we chose to have the current go clockwise. In actuality, the current in the circuit goes counterclockwise. That's all the negative means. So many people believe that as current runs through a resistor that some of this current is used up, and that the current is less after have gone through the resistor. And that's a very common misconception. I hope that I've taught you better in Regents physics to understand that the current doesn't change through the resistor. It's that the resistance in its entirety, or equivalent resistance of the circuit, is what determines the entire current through the circuit itself. But what is used up is energy. I did not mean to do that. So the common misconception that the elements in the circuit use up the current, we know that that is false. But the elements do use up energy. As current goes through, or charge goes through the battery, it does gain energy. It goes to a higher potential. So it's getting more potential energy at the positive terminal. And through a resistor, the energy is dissipated. So this kind of goes hand in hand with what we just learned about Kirchhoff's loop law. We can determine the potential energy in a circuit by looking at the potential difference and the charge within each element. So for a battery, given a specific amount of charge being moved through a potential difference in the battery, we can determine the amount of energy that the charge gains. Ideally, the potential difference of the battery is equal to the electromotive force. However, that's truly not the case in most batteries. Most batteries, and we'll talk about this later too, they have an internal resistance, so they don't actually get the potential that it could have, I guess, is a good word for it. So in terms of an ideal battery, which is what we're using ideal situations for now, the potential energy that's gained by the charge is equal to the charge times the electromotive force, or the most potential that the battery could provide. The rate at which energy is used, you know, is power. Power is du dt, and if we break down the energy in this formula, then we get the charge times the electromotive force, giving you dq dt times the electromotive force, and you know that dq dt is just current. So power is equal to current times the electromotive force. Power, you know, is measured in watts, so not a whole lot that's new here. Okay, so in this example problem, we're given a load of 90 ohms and a source that's providing 120 volts, and we want to know the power that's dissipated in this circuit, or in this resistor. So we are given R, and we are given V. So the power is equal to I times V. But we don't have the current. However, using Ohm's law, P is equal to V over R. I is equal to V over R times V. So we end up deriving a formula for power, which you've seen before, as V squared over R. So we have 120 volts squared divided by the resistance or load, 90 ohms. And you can take a second, pause the video to calculate what that is. Okay, so now you should have arrived at power for this circuit being equal to 160 watts. What? Recalling back to chapter 30, we talked about how the electrons gain kinetic energy by the collisions. They have this, common or collective drift speed. So we talked about all of this in chapter 30. So the energy process through the circuit really is a process of chemical energy, which is provided to the charges, which change the potential energy of the charge, which then in turn is converted into kinetic energy, which is the movement of the charge, which then translates into going through the resistor, which increases the temperature or thermal energy. So through this process, the battery's energy or chemical energy is really converted into heat by going through the resistors, by increasing the temperature of the resistor. So in this example, we have a 100-watt light bulb, which is pretty bright. I think probably in your house you probably use a 40-watt or a 60-watt. Probably should have used that for this example. We want to know what current is drawn from a 120-volt outlet, which is also typical power or voltage out of your home outlets. So we're trying to find the current, I. We have the power, P, and we have the potential difference, V. So we already know this, P equals IV. And so we're just dividing the power by the potential difference and determining the current. Go ahead and do that. Okay, so now you should have arrived at an answer of 0.833 amps, or around that. Because resistors follow Ohm's law, they are ohmic, we can use Ohm's law, I equals V over R, in the power equation to derive more equations for power. And so you can see those equations here. You've also seen this in Regents physics, so you should be familiar with these formulas. Okay, so utilizing these formulas, we have a loudspeaker. The internal resistance of the loudspeaker is 8 ohms. The amplifier it's connected to has a power output of 100 watts. We want to know what the maximum current is through this speaker. So we're trying to find I. We have P and we have R. So using the equations we just had, P equals IV. V is equal to IR, so we have I squared R. Go ahead and calculate the current that's found in this loudspeaker. Okay, so you should have taken the power and the resistance, and square root of that is equal to I. And so we have 100 watts divided by 8, and the square root of that, you should have gotten a current of about 3.54 amps. Kilowatt hours are typically used with energy supply companies like NYSEG or I can't even think of the other ones, not in our area. But kilowatt hours, if you think about a kilowatt is a unit of power, and power is joule per second, and then we're multiplying by time. So the seconds, or the time factor, cancels, and we're really looking at energy. So kilowatt hours are energy usage, and that's what we're billed for. So usually with energy supply companies, they charge a certain amount of money per kilowatt hour, and that's how they determine what you owe on your bill. Okay, so we're going to look at how to add resistors in series, and we already know how to do this, but a little bit about the derivation. We know that the current in the wire is constant, so the current through each of the resistors that are in series is the same. So if we look at the equation, Ohm's law, for the resistance, we're looking at the total resistance is equal to the total voltage, or potential difference, divided by current. So if we look at each individual resistor, each resistor has a change in potential across it, so we'll look at those individually with V1 and V2. If we break out the potential difference into I times R for each of those resistors, we have IR1 plus IR2. You do see that the current cancels in this equation, and we're left with the equivalent resistance equaling the sum of the resistors in series, which is what we determined in Regents physics. So in this example problem, we have a series circuit. There's a 15 ohm, 4 ohm, and 8 ohm in series connected to a 9-volt source. So we're going to determine the change in potential as we go through this series circuit. So as we go from the negative terminal through the battery, the potential of the charge increases. So we have the 9-volt increase, and then we'll go through each of the resistors, and the voltage will decrease, returning us to 0 again. So we want to determine the current first in this series circuit, and then what we're going to do is we're going to graph the changes in potential according to what happens in the elements. So for the current, we want to look at the equivalent resistance of the circuit, so we'll do that first. So REQ is simply adding up the resistors. I'm not going to show much work. We have 15 ohms, 4, and 8. So we have 27 ohms for the equivalent resistance of the circuit. Now that we have the equivalent resistance, we also have the total voltage or change in voltage for the circuit to be 9 volts. So we can simply find the current in the circuit, or total current in the circuit, by dividing that supplied electromotive force from the battery and the equivalent resistance. So we have 9 volts divided by the 27 ohms, and we should end up with 1/3, or 0.33 amps. Repeating. So we're going to take a look at how the voltage changes also through this circuit. We know the current now, so we can determine the potential drops through each of the resistors. So let's first start with the 9 volt. So we're going to go from potential of 0 to 9 volts. So we're just going to have a change there. And we will have no change in potential as we move to the 15 ohm resistor. As we go through the 15 ohm resistor, our voltage will drop. We need to see how much. So in the 15 ohm resistor, we have the change in potential equal to I times R, and we're specific to the 15 ohm resistor in this case. So we have the current, which is 0.33 amps, and we have the resistance of 15 ohms, so we really have 1/3 of 15, which you know is 5 volts. So we're going to decrease by 5 volts, which brings us down to about 4. I'm trying to find where that would be. I'm trying to make my slope also the same. There we go. And then, so we'll just consider a little space between the resistors there, where it's not changing potential. We'll do the same thing for the 4 ohm resistor. And again, we have the 0.33 amp current, as well as the 4 ohm resistor. So we have 1/3 of 4. 1/3 of 4 gives us 1.33 volts. So a little more difficult to get to where that needs to be. So it's a change, so I'll just draw a small change here, 1.3 volts, and then it can come down a little bit further. And then we'll give it some space between where it's not changing potential to the 8 ohm resistor. Do the same thing for the 8 ohm resistor. I times R, 0.33 amps times 8 ohms, so 1/3 of 8. We get 2.7 volts. So we're all the way back to our 0 mark as far as potential difference is concerned. in an ammeter, the current runs through the ammeter, so the ammeter can actually measure the amps. In an ideal ammeter, the resistance is 0. We don't want the device to impede the current at all. We want to measure the current that's within the circuit, and we don't want to have any resistance that affects the total current in the circuit. So the ammeters ideally have a resistance of 0 ohms, and but anything less than like 6 ohms actually works pretty well. So with real batteries, not ideal batteries as we've been using, they have an internal resistance. I did mention that earlier. And we're going to use this in an example. Basically, you can treat this as, this internal resistance of the battery as somewhat of an extra resistor in series with the battery. So it's not that hard. We'll try it. Okay, so for this example, we have a light bulb in a flashlight, has a resistance of 6 ohms, and the 3-volt battery inside has an internal resistance of 1 ohm. We want to know the power dissipated by the bulb and by the battery. So the first thing we want to do is we want to be able to know the current in the circuit. So let's determine what that is. The current is equal to the total potential EMF of the battery, and then we have the equivalent or total resistance of the circuit. So we have a 3-volt battery, ideally, and then we have the total resistance of the circuit in its entirety of 7 ohms. So we find that the current in this flashlight is 4.3 amps. So now that we know the current, we can determine what the power is dissipated by each of those elements. So since the battery has an internal resistance, it will also dissipate power. So the first thing we need to do is determine what the voltage drop is across the 6 ohm resistor. So we can do V equals IR for the resistor to find the change in potential. And we have the current of 0.43 amps and the resistance of 6 ohms. You should find a change in potential for the resistor alone to be 2.6 volts. So now, if we use that 2.6 volts for the potential drop across the resistor, the power outputted by the resistor is just simply I times V. And so we have our current, again, of 0.43 amps, and the potential of 2.6 volts should give us a power output, check it out, of 1.1 watts. So now we want to take a look at what the battery is actually putting out. We know that it should be 2.6 volts, so I just want to show you how that works out as the terminal voltage. So, when changing potential for the battery, we'll put the current in terms of how we derived it before, which is the EMF, total resistance, and then we're going to multiply by the equivalent resistance there. So we end up with our 3 volts over 6 ohms plus 1 ohm equivalent resistance, and then we have our 6 ohm resistor within the circuit. So we still get the same value as the potential that is across the resistor, which does make sense, of 2.6 volts. I also think that there's a better way to do this than described in the text, which is if we found the potential difference across the resistor to be 2.6 volts, and we also found that given that the potential difference supposed to be across the battery was 3 volts, then you know that the voltage the voltage drop across the battery itself is going to be 0.4 volts for a potential drop. across that internal resistance for the battery. That's another good way to determine that potential drop within the battery itself. So the battery is not quite outputting 3 volts, it's actually outputting 2.6 volts. You can determine that by using the current in the circuit, and that's it.